Hey everybody, Trey here. Welcome back to another video. It's been almost 50 years to the day from one of the greatest maritime tragedies in history, and that is the wreck of the Edmund Fitzgerald.
When the gales of November gave her live.
We all know the famous Gordon Lightfoot tune about how the gales of November turned that good ship and true into a bone to be chewed, resulting in the loss of 29 great mariners on Lake Superior back on November 10th, 1975. In this video, we're going to take a deep dive into the meteorology behind the Edmund Fitzgerald's final journey and how such a good ship and crew came to be in such peril on that fateful evening. So without further ado, let's go ahead and get started. First, let's talk briefly about the history of the Edmund Fitzgerald and the events that transpired on that fateful day. As always, I'll put a link to any article I mention in this video in the description box below. For this case, we have some really interesting sources, including the full original accident reports from both the National Transportation Safety Board and the U.S. Coast Guard, which are chock full of useful information. The SS Edmund Fitzgerald made her maiden voyage on September 24, 1958, and at the time was the largest ship on the Great Lakes with a hull 729 feet long and a breadth of 75 feet. With a capacity just over 29,000 U.S. tons, the Edmund Fitzgerald's main purpose was to carry taconite, a type of iron ore, from mines near Duluth, Minnesota to various port cities across the Great Lakes, including Detroit, Michigan, and Toledo, Ohio. To help us go over the details of the wreck of the Edmund Fitzgerald, we're going to use this map loaded into Google Earth. This was adapted from Figure 2 in Holtquist et al. 2006, and each labeled point you see here was collated by an unknown Google user. Shout out to whomever you are. I'll put a link to this collection of points in the description box below. Each point is labeled with the date, either 9 or 10, representing November 9th or November 10th, and the time correlating to each point, which are all in Eastern Standard Time. The Edmund Fitzgerald's final voyage began at about 2:15 p.m. on Sunday, November 9th, 1975. Filled to capacity with over 29,000 U.S. tons or 26,000 imperial tons of taconite pellets, she set sail from Superior, Wisconsin under the command of Captain Ernest McSorley, with her sights set on a steel mill in Detroit. The Fitzgerald, which is the red track you see here, was joined shortly thereafter by another taconite freighter, the SS Arthur M. Anderson, which had set sail at 4:30 p.m. from Two Harbors, Minnesota, en route to Gary, Indiana. The Anderson's track is shown in blue. Initially, the National Weather Service had predicted that a developing storm system over the southern plains would pass just south of Lake Superior by the evening on Monday the 10th, but by 7 p.m. on Sunday evening, the National Weather Service was now forecasting a northward shift in the storm track and issued gale warnings, which call for expected winds from 34 to 47 knots or 39 to 54 miles per hour for the entirety of Lake Superior. Because of the expected rough weather, both the Edmund Fitzgerald and the Arthur M. Anderson decided to depart the recommended shipping route and follow a more northward track to take advantage of the lee created by Isle Royale and the Canadian shoreline of Lake Superior. In other words, because the gales were expected to come from the north, the slightly raised topography of Isle Royale and the geography of the Canadian shoreline would provide a bit of shelter from the winds, also called a lee, so the two ships altered their course to the north to utilize this slight protection, which was not unusual for Great Lakes freighters to do during this kind of weather. Around 1 a.m. on November 10th, the ships encountered rapidly deteriorating conditions with continuous heavy rain, winds of 52 knots or 60 miles an hour, a temperature of 37 degrees Fahrenheit, and waves of up to 10 feet high as reported by the Edmund Fitzgerald, and by 2 a.m. the NWS had upgraded the ongoing gale warnings to storm warnings, meaning expected winds in excess of 48 knots or 55 miles an hour. This continued into the morning. The center of the storm system passed over Lake Superior by 1 p.m. and was accompanied by a brief calm and then a notable wind shift from northeasterly to southerly to northwesterly at about 35 to 50 knots or 40 to 58 miles per hour. At this time, both ships made a turn to the southeast to clear Michipicoten Island to the west, with the Anderson taking a more stark south turn to allow for more space between it and Michipicoten Island given the strong northwesterly winds. By 2:45 p.m. it had started snowing, which, coupled with the increasing winds, reduced visibility. As a result, the Anderson lost sight of the Edmund Fitzgerald, which was 16 miles ahead, and they would never regain visual. The first signs of trouble from the Edmund Fitzgerald came at around 3:30 p.m. when Captain McSorley called the Anderson and told them that they had suffered a down fence rail, lost a couple of vents, and had a noticeable list. Just over a half hour later, Captain McSorley once again radioed the Anderson and relayed that the Fitzgerald had lost both of her radars and requested navigational assistance from the Anderson. Winds continued to increase during this time. The Anderson logged winds of 58 knots or 67 miles per hour just before 5 p.m., the worst of the event, with waves of 12 to 18 feet. Between 5 and 5:30 p.m., Captain McSorley radioed another nearby ship, a Swedish vessel called the Avafors, and advised them that the Fitzgerald had a bad list, had lost both radars, and was taking heavy seas over the deck in some of the worst seas he'd ever experienced. The captain of the Anderson later testified that, as they continued south of Caribou Island, they experienced wind gusts of 70 to 75 knots or 80 to 85 miles per hour, and wave heights had increased to 18 to 25 feet with rogue waves of up to 35 feet. The Anderson continued to advise the Fitzgerald of her position. At about 7:10 p.m., the first mate aboard the Anderson radioed the Fitzgerald to relay the position of another ship about 9 miles ahead of their current location. While signing off, the first mate asked how the Fitzgerald was doing. Captain McSorley answered, "We're holding our own." This was the last message ever transmitted by the Fitzgerald. Visibility improved shortly thereafter as the snow stopped, but the crew aboard the Anderson could only see lights from the distant shore and from other ship traffic, and when they checked their radar for the Fitzgerald 10 minutes after that final transmission, she was nowhere to be found. The Edmund Fitzgerald had sunk at around 7:15 p.m., about 17 miles from the entrance of Whitefish Bay, killing all 29 members of the crew. Alright, now that we've established the timeline and some of the intimate details of the Edmund Fitzgerald's final voyage, let's dive into the meteorology behind this event. We're going to start on the morning of November 9th and go all the way through the evening of the 10th when the wreck occurred. For the first half of the event, we'll be using reanalysis data from the amazing Tornado Archive website, and after that we'll fill in the gaps with some modeling as well as observed data from across the region, including from the ships themselves. Now you might be thinking, Tornado Archive, what does the wreck of the Edmund Fitzgerald have to do with tornadoes? Well, one of the lesser-known meteorological facts about this event is that the day before the accident, November 9th, the day the Fitzgerald and the Anderson began their journeys, there was actually a regional tornado outbreak across the Midwest, particularly in eastern Iowa, which saw multiple EF2s and an EF3 that did significant damage to the town of Waterloo. You'll see why as we go through the data. We'll start out at 500 millibars at 12Z, 7 a.m. Central Time, 8 a.m. Eastern Time on November 9th. I want you to focus on this little shortwave right in here, centered across Colorado into New Mexico. This was our main upper-level synoptic scale forcing mechanism, and it would undergo some significant changes in its geometry over the next several hours. It begins somewhat neutrally tilted and then amplifies and takes on a significant negative tilt as we head into the afternoon on the 9th. We've talked about trough tilt a lot on this channel. Basically, it refers to the orientation of the trough axis. If it's tilted toward the right, as you see in the top example, it is considered positively tilted, and if it's tilted toward the left, as you see in the bottom example, it's considered negatively tilted. While severe weather can occur with any type of trough, negatively tilted troughs are most commonly associated with significant severe weather outbreaks because they result in a much more favorable combination of ingredients. In general, a negatively tilted trough represents a strengthening storm system, and as we've discussed before, what happens in the upper levels of the atmosphere is related to what happens in the lower levels. So a strengthening storm system aloft yields a strengthening area of low pressure at the surface. This leads to stronger low-level warm moist advection beneath cooling aloft, creating ample instability, and the stronger, often more backed surface winds beneath southwesterly flow aloft yields more robust wind shear. This shortwave was moving very rapidly through the main flow. We also see strong flow surrounding the base of the trough coupled with strong defluence in its exit region. Defluence is the spreading apart of the wind vectors in the upper levels of the atmosphere. As we've discussed before, this creates a void, and the atmosphere doesn't like that, so to fill that void, it brings air upward from below, and that's how we get large-scale rising motion in the exit region of many troughs. While defluence aloft is technically supposed to be diagnosed at the 300 millibar level, we can really see it pop on the 500 millibar map. This is at 0Z, 7 p.m. Central Time, 8 p.m. Eastern Time on the 9th, and if we were to draw in some arrows representing the flow across the Midwest, you can really see those wind vectors spreading apart, especially from Iowa and Missouri into Illinois and Indiana, indicative of defluence aloft. Here is the 300 millibar map, valid at 0Z on November 10th, so 8 p.m. Eastern Time on the 9th, and we've shaded in wind speeds where the pinks and purples represent weaker flow and the light blues and greens represent stronger flow. Here's our main jet streak associated with the maturing trough over the Central Plains, but we can also see a separate jet streak extending from the Great Lakes northward into Canada. In between these two is an area of relatively weaker flow, and this helped to create an area of speed divergence, which is simply when an area of faster flow moves away from an area of weaker flow. We can explain this using the analogy of two cars on a highway. If you have a car going 60 miles an hour trailing a car going 100 miles an hour, the lead car is going to move away from the slower car despite moving in the same direction. The same thing happens in the atmosphere. We have 60 knot flow here in the dark blue region and 100 knot flow within the Canadian jet streak. As a result, the flow is going to move apart or diverge, which corresponds to convergence at the surface, a resultant strengthening of the surface low and an increase in large-scale rising motion. This, coupled with the defluence aloft and the significant negative tilt of the upper trough, helped to intensify the surface low from the get-go. Let's go down to the surface and see how things progress there. We're back at 12Z on November 9th. Given that we had strong westerly or southwesterly upper-level flow traversing the higher terrain of the Rockies, we would expect significant lee surface cyclogenesis focused right ahead of the main shortwave, and that's exactly what we got. A surface low developed over the Oklahoma Panhandle early on November 9th, and by the morning of the 9th we had a broad circulation stretching from Kansas all the way down into West Texas. If we look at an analyzed surface map from 12Z on the 9th from Hultquist et al. 2006, we actually had a more defined surface low center in southern Kansas, warm front stretching out to the northeast, cold front down to the south. At this time, the central pressure was about 1,000 millibars. The surface low rapidly deepened as we went through the day on the 9th, thanks to all those aforementioned factors. Widespread 50s and 60s dew points, the greens and blues that you see here, continued to efficiently advect northward as that southerly flow strengthened across the warm sector. The surface low is located along the Iowa-Missouri border by mid-afternoon, and you can just see how the ingredients came together for a regional tornado outbreak. High amplitude, negative tilt trough aloft, deepening surface low helping to strengthen and back those surface winds and pull seasonably high moisture northward, a fairly classic tornado outbreak setup. By 0Z, 7 p.m. Central, 8 p.m. Eastern on the 9th, the surface low had traversed into eastern Iowa, and the central pressure had dropped to about 993 millibars, a 7 millibar drop in 12 hours. The low center was still well removed from Lake Superior, and it wasn't until late evening into the very early morning hours of the 10th that the ships began to experience deteriorating conditions. The ships would have likely started feeling a notable increase in wind speeds by late afternoon or early evening, and that is because of the increasing pressure gradient over the lake. As we've discussed before, the pressure gradient is the change in pressure over a given distance. If the pressure is changing a lot over a short distance, the pressure gradient will be high, and because the pressure gradient modulates wind speeds, the wind speeds would increase. And that's exactly what we had going on at this time. Here's our area of low pressure centered over Kansas City by early afternoon, much higher pressures from Lake Superior northward into Canada. As the deepening low pressure made its way northeast, the pressure gradient tightened substantially as evidenced by the decrease in spacing between the isobars over Lake Superior, and the winds began to increase. The Edmund Fitzgerald reported north-northeasterly winds of 52 knots or 60 miles an hour at 1 a.m. Eastern, about 20 miles south of Isle Royale. This may be slightly overestimated as other ships in the area reported winds of around 40 miles an hour at this time, but nonetheless that's still quite strong and the winds were certainly on the rise. The Fitzgerald also reported continuous heavy rain at this time. This matches well with the precipitation distribution around a typical mid-latitude cyclone. Let's focus on the area along and north of the warm front in a typical mid-latitude cyclone, an example of which you see here. The warm air advected northward along a strong southerly flow in the warm sector tends to ride up and over the cooler air to the north, a process called overrunning. As we know, frontal zones don't just manifest themselves at the surface, they slope upward into the atmosphere. Given the more gradual slope of a warm front versus a cold front, you get a very broad area of rising air leading to a generally widespread area of stratiform rain, in other words, non-convective rain due to the stable air north of the warm front. If the vertical temperature profiles are supportive, you can also have freezing rain or snow north of the warm front. And with the coldest air generally wrapped around the northern and western sides of the surface low, snow, often heavy, tends to occur there. The intensity of the precipitation also increases as you get closer to the center of the surface low, where surface convergence and therefore upward motion is maximized. If we take a look at Lake Superior's location in relation to the surface low, you'll see it's right in that area north of the warm front and low center, certainly in that favored area for precipitation given strong southerly flow overrunning the warm front, and given their location with respect to the track of the low, the Fitzgerald and Anderson would likely remain in precipitation for quite some time. The rain continued and the pressure gradient continued to tighten over Lake Superior as the low deepened and moved closer, maintaining very strong winds over the lake. By 7 a.m. Eastern on the 10th, the low was situated over the upper peninsula of Michigan, closing in on Lake Superior, and its central pressure had plummeted to 982 millibars, an 8 millibar drop since 1 a.m. and an 18 millibar drop since 7 a.m. the previous day. This is equivalent to a typical Category 1 hurricane. Of course, we're comparing apples to oranges by comparing an extratropical cyclone to a tropical cyclone, but you get the idea. This low was deepening very rapidly and efficiently given the very favorable environment. The 500 millibar trough maintained its high amplitude negatively tilted nature as it progressed to the northeast, coupled with the strong defluence and divergence aloft, a textbook recipe for the intensification of a mid-latitude cyclone. In fact, the 18 millibar drop in 24 hours comes very close to meeting the criteria for bombogenesis at this latitude. By this time, the surface low was also beginning its occlusion process. This happens when the cold front catches up to the warm front and begins to displace the warm air off the surface. The beginning of the occlusion process often signals peak maturity of a cyclone, but in this case the low continued to deepen well after occlusion began, although at a much slower pace. By 1 p.m. Eastern on the 10th, the central pressure had fallen to 980 millibars. The center of the low passed over Lake Superior just west of Michipicoten Island by late morning to midday on the 10th. As mentioned earlier, the Fitzgerald and the Anderson experienced a notable wind shift around this time, from strong northeasterly to weak southerly to strong northwesterly, coincident with their turn to the southeast. The two ships were very close to the center of the low at this time, which would explain why they felt a brief calm as the winds turned out of the south. Similar to a hurricane, the winds at the center of a mid-latitude cyclone tend to be weaker than in surrounding areas where the pressure gradient is much stronger. They then emerged on the backside of the low, where winds turned out of the northwest and conditions began to rapidly deteriorate once again. Notice how the pressure gradient on the backside of the low was even tighter than that on the front side. The isobars are spaced even more closely together, meaning that the strongest winds of the entire event were moving in from the west. In addition, much colder air aloft began to funnel in as the upper trough continued to move to the northeast and the surface low moved into Canada. This had a couple of important impacts. Number one, it began to snow over the lake at about 2:45 p.m., further reducing visibility. And number two, it increased the temperature difference between the air aloft and the water temperature on the surface of Lake Superior. This likely induced vigorous vertical mixing, very similar to how strong surface heating initiates vertical mixing as we discuss in many severe weather setups. The increasing temperature gradient between the warmer lake surface and the colder air aloft would allow surface air to rise, but also bring air from aloft down to the surface. Therefore, intense low-level winds were likely mixed down to the surface with very little reduction in speed, helping enhance the already strong winds that were a product of the tightening pressure gradient. Also, the terrain of the southern coast of Lake Superior may have played a role in enhancing the winds as well. This area here is home to an area of higher terrain known as the Huron Mountains. In this northwesterly flow regime post-surface low passage, we likely had a phenomenon called coastal convergence as a result of the geography of this portion of the coast. Coastal convergence is the result of the difference in friction between the open lake waters and the land. Intuitively, there's much less friction or drag on the wind over open water, but the much rougher land surface, especially with a higher terrain feature like the Huron Mountains, provides a lot more friction or drag that slows the flow down. We talked about this in the upper levels of the atmosphere, but we can also apply it to surface winds in this situation. Faster winds over water moving into an area of slower winds over land yields convergence along the coast, and once those winds make it to the other side of the landmass into open waters once again, especially when the wind is blowing at small angles to the coastline, the flow accelerates due to the sudden decrease in friction or drag. Another piece to this coastal convergence phenomenon is the fact that winds tend to converge as they are forced around landmasses, as illustrated in this graphic. The Keweenaw Peninsula, this landmass that juts out into southern Lake Superior, forces northwesterly winds around it, and they tend to converge on the northern and eastern sides of the peninsula's tip. This convergence and acceleration of the flow due to the coastal geography likely enhanced the winds as well, especially across the southern half of Lake Superior where a distinct wind maximum developed in the afternoon on November 10th. This is illustrated nicely in this simulation from Holtquist et al. 2006, available on the NWS Marquette page on the Edmund Fitzgerald disaster. They took all of the weather observations throughout the event, including those from land-based observation stations and those from the ships themselves, and ran them through a weather model to estimate the wind speeds across the lake and fill in some of those gaps in the historical dataset. The Fitzgerald, which is denoted by the blue X, started off her journey on the afternoon of the 9th under fairly quiescent conditions. Winds started to pick up that evening and even more so into the morning hours of the 10th. Here comes the approach of the surface low, bringing with it a brief respite as it passes over the Fitzgerald around 10 a.m., and then by 1 p.m. the winds flip to northwesterly and we start to see this area of enhanced wind develop across southern portions of the lake, north and east of the Huron Mountains. The pressure gradient on the backside of the low continued to tighten and, coupled with the impacts of vertical mixing and terrain, the area of strong winds across southern Lake Superior began to intensify and expand eastward toward the Fitzgerald and the Anderson. There was also a secondary wind maximum extending from the northern tip of the Keweenaw Peninsula. This maximum and the maximum east of the Huron Mountains appeared to coalesce into one large wind maximum of 45 plus knots by 7 p.m., just before the accident. You can see that the Edmund Fitzgerald was on the eastern edge but still well within the area of strongest winds, which were the most intense of the event, with the Anderson's captain recounting winds of 70 to 75 knots or 80 to 85 miles per hour, as they moved south of Caribou Island after 5 p.m. Of course, the rapidly increasing winds had a profound impact on the heights of the waves on Lake Superior. Here's another simulation from Holtquist et al. 2006 showing the modeled progression of wave heights throughout the event. The location of the Edmund Fitzgerald is the blue plus sign. We start to see an increase in wave heights to about 3 to 4 meters, or about 10 to 12 feet, as the winds first began to increase on the evening of the 9th into the morning of the 10th. They subsequently settled down as the winds decreased with the surface low passage and then promptly increased as the northwesterly winds took hold by early afternoon. By 4 p.m., maximum wave heights were estimated to be about 7 meters, or about 23 feet, and that was quickly moving into the area for which the Edmund Fitzgerald was heading. As the winds reached their peak around 7 p.m. just before the wreck, so did wave heights, approaching 8 meters, or about 26 feet, in the area where the Edmund Fitzgerald was. This simulation also determined that 1 out of every 100 waves in these conditions could reach about 11 meters, or about 36 feet, and 1 out of every 1,000 waves could reach 14 meters, or 46 feet, in height. This was problematic for a number of reasons. First, the Fitzgerald had already begun to experience structural damage by this time, and the extremely tall waves no doubt exacerbated the issue she was facing by continually flooding the ship with water. Second, the wind was pushing the waves basically from west to east, which may have induced a dangerous rolling motion in the Edmund Fitzgerald, which was traveling southeast. In other words, the waves were hitting the ship from the side, which likely caused the already compromised Fitzgerald to struggle even further. Finally, the fetch of the waves in this northwesterly or westerly flow regime was significantly greater than earlier on in the journey when the winds were out of the northeast. For those not familiar, the fetch is simply the length over which wind and, in turn, waves can travel over open water without obstruction. So earlier on in the Fitzgerald's journey, for example, the early morning hours of the 10th, the wind was out of the northeast, meaning that the distance the waves could use to build up in size before they reached the Fitzgerald was relatively short, essentially from the northern shoreline of Lake Superior to the Fitzgerald along the path of the winds. Compare that to around 7 p.m. on the 10th, just before the accident. The winds were now out of the west-northwest, so the waves now had almost the entire length of the lake to use to build and build and build before they reached the Fitzgerald, meaning much taller waves impacting the two ships. So really, the Fitzgerald was in the worst possible place it could have been on the lake during this time as the winds and waves maximized. If the Fitzgerald would have been on the northern part of the lake during this time, it would have still been quite windy, but the fetch wouldn't have been nearly as long, meaning that they wouldn't have had to deal with such monstrous waves, and in all likelihood this tragedy may have been avoided. There's also some speculation that a phenomenon called the Three Sisters may have played a role in the wreck of the Edmund Fitzgerald. The Three Sisters are a series of 3 consecutive rogue waves, which are waves that are unusually large and appear suddenly, and recent research has shown that they often form on Lake Superior. These waves can be especially dangerous to ships because the first wave introduces a large amount of water onto the deck, and before it can drain off, the second rogue wave hits and exacerbates the problem. This repeats itself when the third wave hits and the rapidly accumulating water can overload the deck. In his testimony after the accident, the captain of the Anderson reported that his ship was hit by 2 rogue waves of 30 to 35 feet around 6:30 p.m., the first of which inundated the rear cabins and damaged a lifeboat, and the second of which came over the bridge deck. He noted that these 2 waves, possibly followed by a third, continued in the direction of the Fitzgerald and would have impacted her around the time she sank, which would have only worsened the issues she was facing and could have been the straw that broke the camel's back, if you will. Taking a final look at the background pattern at the time of the accident, the 500 millibar trough was well off to the east, and the surface low had continued off to the northeast toward James Bay in Canada. It had deepened to about 978 millibars by this point, and the pressure gradient was still extremely tight on its backside, as we discussed. So just how unusual was this storm system? It's not uncommon to see intense storms impact the Great Lakes, especially during the fall season. So was this one particularly unique? Well, Holtquist et al. 2006 found that storms of similar intensity and characteristics to the November 1975 storm happen on Lake Superior every 2 to 6 years on average. When examining wind climatology on Lake Superior, they also found that sustained winds of 50 knots or 58 miles per hour happen roughly every 2 years, and sustained winds of 65 knots or 75 miles per hour happen roughly every 20 years on average. So while the conditions experienced by the Edmund Fitzgerald are not necessarily a frequent occurrence, they are also not necessarily rare. However, the characteristics of the waves on that fateful night were quite unusual. Holtquist et al. 2006 found that significant waves over 7 meters or 23 feet tall occur on Lake Superior at a frequency of only 0.1% of the time, and nearly all of these travel from north to south. There have been virtually no waves over 7 meters tall that have been found to move from west to east on Lake Superior as they were on the night of the accident. Therefore, it's not surprising that Captain McSorley stated that the waves encountered by the Fitzgerald that night were some of the worst he'd ever experienced, as it was a phenomenon he'd likely never seen before. So all in all, the wreck of the Edmund Fitzgerald was the result of a confluence of unfavorable occurrences. She was in the wrong place at the wrong time as it comes to the weather, as the most severe conditions of the event took place as the Fitzgerald was in the area of Lake Superior most susceptible to those conditions, the eastern edge of the strongest winds, at times hurricane force, and the fetch that the resultant waves took advantage of turned them into 35-foot tall behemoths that had likely never been seen before. If the Fitzgerald had left Superior, Wisconsin just 6 hours earlier or later, they would have missed the worst of the storm and this maritime tragedy would have been avoided. Along with the obvious impacts from the weather and waves, there have been some other hypotheses thrown around about the causes of the accident. The NTSB concluded that the Fitzgerald experienced significant and sudden flooding of the cargo hold due to the collapse of one or more cargo hatch covers from massive amounts of water coming aboard. These hatch covers were not weathertight to begin with and had allowed water to enter the cargo hold over an extended period. Multiple entities also postulated that the Fitzgerald may have accidentally run aground on a shoal, which would have damaged the hull and induced flooding of the cargo hold. However, this was rebuked by the NTSB as there was no evidence of gouges, scrapes, or fractures on the bottom plating of the hull, consistent with a grounding event. While we may never know the exact cause of the accident from a structural perspective, hopefully this video gave you some good insight into the intense weather conditions at play on the Edmund Fitzgerald's final journey. Lake Superior never gives up her dead when the gales of November come early, and we remember the 29 lives lost on that fateful night 48 years ago today.